So I want to take you through, obviously tidal disruption events occur around supermassive black holes. And for that, so some of the things that are pretty important is actually the GR effect. The most basic GR effect that's important in a tidal disruption event is that sort of precession of the perihelion of Mercury. So you get a star passing around a black hole, but rather than doing a Keplerian orbit, that orbit will precess. And that's very important for TDEs because it leads to the self-intersection of the stream and therefore initiates the accretion onto the black hole. So that's kind of the motivation behind why we need to do things in relativity. Also, we got speeds moving close to the speed of light. So the question is, what's different? So what is different? Sorry, my pen just has a few issues. So what is different when velocity goes to the speed of light? So you may or may not know what we mean by regular hydrodynamics. So if we're Newtonian, then we simply solve a set of coupled partial differential equations. So for example, we solve the continuity of the continuity equation, which expresses conservation of mass. We express the acceleration of the fluid or of a fluid parcel with the momentum equation. And so that's driven by a pressure gradient and any kind of gravitational interaction. And then we have like an energy equation, for example. For example, we say the total energy of the fluid is conserved. And that gives us a term that looks something like minus grad of PV over rho. And that's basically expressing conservation of mass, momentum, and energy. So I'd say you're like hands up if you've seen those equations before. I'm taking that as everybody's got their hands up. But it's like shouting into the void, so we'll carry on. But you can message in the chat if you really want to give some feedback. And coupled with that, so if we want to solve the gravitational force, which is obviously important if you want to think about star swinging around a black hole, there's two kind of gravitational components involved. So there's the gravity of the star on itself, so the star holding itself together, but there's also the gravitational potential from the central object. So in Newtonian gravity, for example, we would say, for example, that the gravity of the black hole is given by, minus gm over r, for example, which is, but then we'd have to calculate the self-gravity of the star from Poisson's equation, which gives us, knowing the density distribution of the star, that gives us the gravitational potential, and then we can put that back in our Newtonian equation to give us the gravitational interaction. Okay, so what's different in GR? Well, not much actually. So it turns out, GR can be complicated by a lot of mathematics, but you can also make it seem pretty much the same as regular fluid dynamics. And the only thing that really changes is that you have a slightly different definition of variables. So for example, the conserved mass is not just the density. It's a kind of conserved density that I'll explain in a minute. We usually write things with tensors. You don't need to know anything about tensors right now. Only that when you have a repeated index like that, so dvi dxi is exactly equivalent to our like div v over on the left here. Okay, so what's different in the momentum equation? Well, what we call velocity in Newtonian fluid dynamics actually becomes the momentum per unit mass. Now, momentum per unit mass in a Newtonian fluid is just the velocity, but in relativity, the momentum, actually, let's not call it a vector, let's use tensor indices. So it's a pi, which means there's three numbers, same as velocity, but the ups and downs become important in GR. So it's 1 over rho star. Again, so pressure gradient, just the same. There's a square root of G, which I'll explain in a minute. But other than that, that's just simply the pressure gradient, just the same. And then this minus grad phi term becomes, in GR, it becomes the derivative of the metric. So the metric is something that takes the place of the gravitational potential. T mu nu is the stress energy tensor, which if you've done a GR course will become familiar to you. And dg mu nu dxi is like the place of grad phi over here is the spatial derivative of the metric, which is the thing that describes the curvature of space-time. Okay, so then the energy equation, sorry, let's go from there. Our energy equation becomes dE dt, and again, it has the same form, expressed in a slightly more GRE way. d dxi square root of G minus GP. So square root of minus G is actually the determinant of the spatial metric. So again, that's just a thing that can be computed by knowing that this G mu nu term here. Then we can calculate this minus square root of G. And in all the simulations we do, that's actually 1 anyway, because you can always choose a set of Cartesian coordinates. And there's a VI in there, because that's the energy equation. And then you have a minus sign, but the same kind of term as you had in the momentum equation. But obviously in this is a term that could become important if the metric is time dependent. So if the metric is time dependent, that would change the energy of the fluid, and that comes in as a dg mu nu dt term, where you had a g mu nu dxi term in the momentum. Okay, so again, sort of audience question. Is anyone in the chat? If anyone can put anything in the chat as audience response. So what do we do to replace the Poisson equation in GR? So what does this become? Does anybody know? I'm going to leave a short, uncomfortable pause. Well, let's see if we got any answers in the chat over here. No? Okay. Let's go back to our uncomfortable pause. Okay, so our Poisson equation is the equivalent in GR of the Einstein field equation. So if we want to know what the metric is, so the lazy way of writing that is just G mu nu is 8 pi G T mu nu. So in GR, we sort of always start to assume that the speed of light is 1. So we say the speed of light is 1, which is just a choice of units. So in general, instead of a Poisson equation, which is already kind of complicated to solve, we have this set of 10 coupled partial differential equations, or there's 16, but reduced to 10, which are a giant mess. So the procedure for solving for the metric from any general spacetime is known as numerical relativity. So numerical relativity exists, it's a thing, but it's kind of a separate discussion to once you've got the metric, how do you do hydrodynamics? And that answer is this kind of business that we've already described. Okay, so let's just sort of summarize the key aspects. So the key aspects are, first of all, we haven't actually defined what these variables are. So number one is we must define the corresponding conserved quantities. So you can think of density, for example, is the conserved mass per unit volume. So the conserved mass, momentum, and energy. Okay, and in GR, these are different. So these differ from the Newtonian counterparts. So where we had density, velocity, and energy before, now we have these things that I've called rho star, momentum, pi, and energy. So they carry the same meaning. They are mass, momentum, and energy, but they are much more complicated variables. But you'll notice on the right-hand side of our equations up here, so if we scroll back a little bit, we actually need things like pressure, velocity. So pressure comes from what we call the primitive density, which is this quantity on the left. And we have velocity, for example. So we need some kind of procedure. So the new thing is that we require a procedure to solve for what we call the primitive quantities, rho, v, and e, from the things we evolve on the left-hand side of our equations. And I should add up here, actually. So this d dt is the Lagrangian time derivative. So the definition of that is a partial time derivative plus a v dot grad. So the Newtonian way of writing that would be v dot grad. So for example, if you like have d rho dt, that would be d rho dt of v dot grad rho. So sometimes if you're used to fluid dynamics, you would see that all kind of written out on the left-hand side. So Lagrangian way just gives you a way to simplify what's going on in the time sense. And when we do that in SPH, which is the method we use, We get it kind of for free because we actually move the particles with dx dt equals v. So we have a set of particles that are Lagrangian points. That means these time derivatives actually tell you how those quantities evolve on those particular set of particles. Does that make sense? Okay, so we need to solve for this procedure. So we need to have the definition of these things from from rho, pi, and e. Okay, and so the third complication is that, so our Newtonian gravitational force which was just minus grad phi, is replaced by gradients of the metric. Okay, so what are the gradients of the metric? Well, that's our dg mu nu. Sorry, pen's not working. dxi. All right, so the similar kind of term. So whether you've done GR or not, well, hopefully you've done at least some special relativity. So you recall, for example, that when you define a metric, it's this line element. So it's a difference in distance between 2 points in space and time. And the definition is you kind of have this, again, with the repeated index implying a summation, dx mu, dx nu. So for example, the Minkowski metric is the metric of special relativity. You would say that ds squared, so this describes a flat space, is minus c squared dt squared plus dx squared plus dy squared plus dz squared. And so in that case, our metric would be just a Minkowski metric, so it would be a minus 1, 1, 1, 1 along diagonals and 0 elsewhere. So hopefully you remember a little bit of that, or you learned a little bit of that in your either undergraduate or PhD studies. And so this is one, for example, is called the Minkowski metric. So in that case, so we say that just describes a flat space-time. You can think for yourself, what would the gradients of the metric be in that case? I'm going to pause for your answer. Your answer should be 0. Yeah, and so in the case of Minkowski metric, we're describing a flat space-time, and that means so gravitational forces, if you want to call them that. So in GR, they're not necessarily forces, they're just gradients in the spatial metric, and you're just following straight lines. So in this case, gravitational forces are 0, and you can see how that arises in our fluid equations because the metric gradients that appear as the kind of gravitational terms, this is the equivalent of minus grad phi, is therefore 0 in flat space. Okay, so we need to know what the metric is, obviously, to be able to study how a fluid behaves. Okay, so maybe obvious to state, but I'll state the obvious. So we adopt standard GR conventions. So whereas you can choose a different set of units for a Newtonian fluid. So for example, I've already used the Einstein summation convention. So for example, what does that mean? It means that, for example, dvi dxi is equivalent to like the sum of over I dvi dxi, but we don't need to write the summation because whenever you have an index that's up and down at the same time, then that kind of implies that the summation is present. And so that would be equal to, if you sum from I equals 1 to 3, which is the usual practice, that would be like a dvx dx plus plus dvy dy plus dvz dz. All right, so that's just a GR way of writing like divergence of velocity, which again is independent of the coordinate system, but those sort of things are kind of assumed in the way that we've already written our equations. For example, we have a d dxi of vi, so that's like a divergence, just like we have the divergence of dot with PV. So that becomes a scalar quantity, and again, because the index is repeated here, up here we have an I and an I, so that repeated index implies that it's a summation, which is equivalent to the dot product here in the vector equations. So hopefully that's clear. Okay, so the question is, how do we get the metric? So in general, we must solve the Einstein's equations. To get the metric. So what are Einstein's equations? Remember, well, so what sits on the right-hand side is that T mu nu. So we haven't defined that yet. So the thing on the right-hand side of Einstein's equations is the stress energy tensor. So for a perfect fluid, T mu nu is given by basically rho c squared plus rho u plus p. U is the internal energy per unit mass. And this thing is the fall velocity. And P times the pressure times the spatial metric. So in general, to know the right-hand side of our Einstein equations, we need to know the density, we need to know the internal energy, we need to know the pressure, we need to know the velocity, and we need to know P, but we also need to know the metric itself. So that's a little weird because Einstein's equations become very complicated because the right-hand side, kind of gravity is involved on the right-hand side as a source term. So gravity kind of gives gravity, which is a bit weird, but okay. So same, you can obviously go up and down and you get the same thing. So rho c squared plus rho u plus p, and you can get the lowering operator that gets you the lowered fall velocities, p g mu nu. So that's the one we used above. We had T mu nu here with the lowered thing, and we can see that appears with the uppercase, for example, as the prefix to our dg mu nu dxi term. Okay, so that's what we need on the left-hand side. And let's just define a few things. So u mu here is the fall velocity. So what's the fall velocity? Well, it's dx mu d tau. So tau is the proper time. And so we have a velocity, which is v mu, and that's dx mu dt. So that's what we mean by, we're taking derivatives with respect to coordinate time, which we call t here, dt, dt, dt. And that is not the same as proper time. Okay, so the velocity that we're talking about and that we move our particles with is this v mu. So obviously, since u mu is therefore u naught v mu. What's u naught? So u naught is therefore dt d tau, because the naught component is the time component. Then we have everything we need. So that's just basically a velocity term times this dt d tau. Okay, so our T mu nu relates to our what we call our primitive quantities, which are rho, v, and u, and pressure. Okay, so remember that in general, to solve Einstein's equations, we've evolved these variables, we need to solve for these ones, and we could simply put them on the right-hand side of Einstein's equations and then run it through a numerical relativity solver and get the metric. So we have recently done that, but for tidal disruptions, that's kind of unnecessary. So we can simplify matters by using exact solutions to Einstein's equations. What's the exact solution we have in mind? So hopefully a few of you should already know this. So for example, what would a point mass in Newtonian gravity give you as a gravitational potential? I'll leave you to think about it for 2 seconds. So we don't have to solve Poisson's equation in this case. We can simply write down that the gravitational potential of a point mass is minus gm over r. So for example, I already wrote that down way earlier. Said if we wanted to simulate Newtonian tidal disruption event around a black hole, we could simply use the Newtonian gravitational potential, m black hole over r. And that's simply the exact solution to Poisson's equation for a single point mass object. All right, so what is the equivalent of that in general relativity? Did I hear you say Schwarz and Child? Schwarzschild, if you pronounce your German correctly. So the Schwarzschild metric is the equivalent of that minus GM1R for the Einstein equations. Okay, so the simplest solution to Einstein equations for a point mass is this. So I'll keep the c squareds in there just for a second. But in general, we can assume that c is 1 in GR, and that just means our velocity is always in units of the speed of light. And dr squared, 1 minus 2 gm on rc squared, plus r squared d theta squared, plus sine squared theta d phi squared, in bracket. Okay, and you should recall, or you may not recall yet, but if you take some GR later in your honors or whatever year you're up to, you'll know that this ds squared, which is a distance, like a proper distance, can be related to a proper time interval by minus c squared d tau squared. Okay, so all right, so Schwarzschild metric looks fine. So it might make more sense when we're simulating a fluid like this, if we want its gradients, to simply write that in Cartesian coordinates. So you've probably seen the Schwarzschild metric before, or if you've seen the Schwarzschild metric at all, it's usually written in that form. So in Cartesian coordinates, which is the way we usually use it, there's no reason to use spherical coordinates. Also because Cartesians are much more general. With c equals 1, then our g mu nu would look something like this. So we have a minus f on the time component. We have zeros on the g tx components, because there's no spin in the Schwarzschild metric. So in a Kerr metric, you would end up with non-zero terms here. So this is like a 1 minus 2m over r cubed, y squared plus z squared. And the other terms are similar. So for example, so you do get some little terms here, like an xy over f 2m over r cubed. And the same thing here, like a xy over f 2m over r cubed. And so on. So this sort of continues, but you get an x squared plus z squared here. So this is merely to illustrate that it's it's reasonably straightforward to write down the Schwarzschild metric in Cartesian coordinates. And so hence the terms that we need for the gravity from the black hole, so we can easily compute the dg mu nu dxi terms that we need. And you might be thinking to yourself, well, if I can do an orbit around a black hole, if you've done a GR course, which I'm not expecting everyone to have done, but if you have, you'll notice, well, isn't this just the geodesic equations? So indeed, if we just take these components of our fluid equations, that is just a fancy way of writing the geodesic equations. So you take the d momentum dt equals dg mu nu dxi, and that just tells you basically how you do orbits in the Schwarzschild metric. So what's really nice here about our approach to fluid dynamics is that if we take the pressure out of it, we can simply simulate the orbits of point mass particles, for example, around a Schwarzschild black hole. We can see those effects of precession, and we can test that the GR orbital motion is correct and matches analytic solutions, for example, for the speed of an orbit, for example, in the Schwarzschild metric. So you can do the kind of n-body simulation before you start thinking about fluids. So also, so I should say F here is defined as this 1 minus 2 gm over rc squared term, possibly to the -1. No, that's right. Yeah, that's that term. Okay, so the square root of g is 1, which is the determinant of the metric. So you've got something like a matrix. You can take its determinant. But in Cartesian coordinates, that square root of minus g is 1. It would be not 1 in spherical coordinates. So that's just like saying, if I want to integrate over the volume, then, if you integrate, instead of integrating some, density, so it's like saying if I want density dv, then in Cartesians, that's equal to density, dx, dy, dz. But if I'm not in Cartesians, that's equal to, so let's call this a triple integral. But if I want to do that in spherical coordinates, then it's not just dr, d theta, d phi. You have a determinant here, and that determinant is the minus g. So that's the equivalent of this. So that's the equivalent of what you know and love from integrating things in different coordinate systems. That's the role that the minus square root of g plays in our fluid equations, right? So you can see how that comes about. Because these equations up here are completely coordinate independent, means we could choose our simulation to be in spherical coordinates, or we could choose it to be in Cartesian coordinates. Cartesian coordinates is convenient because it just makes this square root of minus g terms 1 everywhere. Okay, but there's no reason why you couldn't choose spherical coordinates if you wanted to. All right, so let's talk about the quantities themselves. Hopefully you're still following. So conserved quantities. And I just want to give you a flavor of how we arrive at this, this kind of thing. So, for example, mass conservation. So why do we arrive at this variable rho star? So the conserved quantity in Newtonian physics is the integral of density over the volume. So what's different in GR? Well, we have to be able to deal with the general coordinate system thing. So obviously in GR, we're obviously going to need rho square root of minus g, let's call it, well, d cubed r. For a general coordinate system, that's going to be like the conserved integral. So you can already see that, if we could define a density variable, say rho star, that would be equal to rho square root of minus g. We could make our integral look the same as it did before. And we're just defining a new variable. So that's sort of the idea. So similarly, so sometimes we think about, when you get close to going to the speed of light, you can think about, so you don't increase your speed anymore, but you do continue to increase your momentum. So it's hard to get something to the speed of light because one way of thinking about that is the mass of the object increases. Mass is not actually a very helpful way to think about it, but we are thinking about conserved mass. So if we think about considering special relativity, then you know that the conserved mass would be something like integral rho gamma dv, where gamma is the Lorentz factor, so that's 1 over the square root of 1 minus v squared over c squared. And that in GR is equivalent to this dt d tau. So that's like a u naught, basically, as defined up above. So if you remember that u naught is dt d tau up here. So that is essentially the same role as the Lorentz factor in special relativity. Okay, so in GR, so we generalize to, so this mass conservation becomes something like, so you can see we take into account the general coordinate system and the gamma from special relativity, which becomes a u naught and a minus g, and that gives us a conserved integral that looks something like that. So you can call it dv. I mean, it really means dv is a little loose. What we really mean is d cubed x in terms of like our coordinate choice. Okay, so that one means we can, so hence we can define rho star is by definition then this combination of variables. So it's the primitive density times u naught and a square root of minus g, and that will give us a conserved mass variable. Okay, so that is the variable that we used up in the top set of equations that replaced our density in the Newtonian case. So I hope that makes sense. So the idea is to still, basically express the same conservation laws, but the quantities that are conserved are sort of a more general thing than just density, velocity, and energy. So it really is the conserved mass per unit volume, the conserved momentum per unit volume, and the conserved energy per unit volume that we want to adopt. So some nasties in here already. So if you think about what dt d tau is, so for example, you know that d tau squared, so I said before minus c squared d tau squared is equal to g mu nu dx mu dx nu. That's just our definition of the metric. So if we want to find dt d tau, so dt d tau squared, and I'm going to drop the c for a minute, is equal to minus g mu nu dx mu dt dx nu dt. So those are just our velocities. So that's equal to minus g mu nu v mu v nu. And there are just our primitive velocities that we defined before. So that's just our velocity from a few moments ago. Here, that's our definition of a velocity. It's the derivative of the position with respect to the coordinate time. Okay, so what's nasty about this is that if I want to solve backwards for my conserved density, from my primitive density from the conserved density, then I need to know what the velocity is. How do I get the velocity? Well, I don't have velocity. What I have is momentum and I have energy, but I don't have velocity. So you can see that this procedure of solving backwards for the primitive quantities from the conservative quantities is actually a bit of a mess. And actually, that's the main thing that complicates the GR code. So similarly, and I'm going to skip the details of how we get to this, to these variables, but it's the same kind of principles as with the mass. So the conserved momentum is U naught, W, and I'll explain W in a second, G I mu, V mu. So it has to be a lowered variable. So W is this enthalpy variable, which is 1 plus rho, 1 plus U, the internal energy per unit mass, plus P on rho. So you can already see there's a bit of a problem there too. So for example, if we want to solve backwards for velocity from momentum, obviously that's U naught's a giant mess that involves a velocity. But we've also got this W term, and that involves the pressure and the internal energy. So it involves the energy equation. So there's, there's a big complicated mess that you have to solve for backwards. And finally, we have the energy. So the energy is basically the dot product of the velocity with the conserved momentum, and then 1 plus the internal energy over U naught is about the simplest way to write down the conserved energy per unit volume in GR. Okay, but we just need to realize that these variables are just the more general version of our conserved quantities. Okay, so I would just add a note that you can then derive these conserved quantities. In fact, you can derive the whole set of equations by starting with a Lagrangian. So some of you will know what a Lagrangian is, some of them won't. But so the way you derive a Lagrangian, so the Lagrangian for deriving the fluid equations in GR is this expression, T mu nu U mu U nu dV. And the way you derive equations from Lagrangian is you say, well, ddt of dl dvi, for example, equals dl dxi. So in principle, the mathematics is a little bit complicated, but you can derive your equations of motion from the Euler-Lagrange equations, just in the same way that you can do it for example, deriving the geodesic equations, Lagrange equations. And it's a little bit deeper than that, so that's why I just want to mention it. For example, the conserved momentum is kind of by definition is the derivative of the Lagrangian with respect to the velocity. So this momentum variable didn't arrive from nowhere. It comes from expanding this Lagrangian, taking the derivative with respect to the velocity, and that kind of defines what you call the canonical momentum. Canonical, when my pen works, momentum. So it's, you know, it's quite elegant, actually, the way you describe these variables. All right, so just the final thing that we need to cover then. So you might notice we've missed a piece of gravity. So if you can murmur to yourselves what that might be. So we've described how to write down the fluid equations. We've described that in general, we'd need to solve the Einstein equations to get the metric, but that for a tidal disruption event, we say, well, mostly we need the gravity from the supermassive black hole. We've got this procedure we need to solve for PE rho density, velocity, and internal energy from the conserved energy, momentum, and the conserved density. But what's the piece that we've missed? So let's come to this. So my pen's having issues. It's the Queensland warmth. Okay, so let's take, you know, a star like the sun. It's, you know, having a close encounter with the black hole. So what's the problem with just considering the gravity from the black hole? Murmur amongst yourselves. But the issue is, well, we need the star to hold itself together when it's a long way from the black hole. So you may have learned already. So the key thing for tidal disruption is that you have this tidal radius, which is the radius of the star times the mass of the black hole over m star. Oh, let me get this the right way around. So it's an equivalent density thing. So you say the mass of the black hole, r tidal cubed, is equivalent to mass of the star, r star cubed. So it's like saying the densities of the two bodies are equal, where the gravity of the black hole becomes more important differentially than the gravity of the star. So that gives us that r tidal is m star over m black hole. M star over m black hole to the 1/3. Okay, so but outside the tidal radius, then the self-gravity of the star, then the self-gravity of the star is the necessary thing of the star is important by definition of the tidal radius, because that's what we're saying. The gravity of the black hole is dominant inside some kind of volume, but outside that volume, it's the black hole gravity that's the important thing. But we just said, in general, if we want to solve the gravitational interaction, we need to know the metric. But the only way to know the metric is to solve the Einstein equations, and that's a giant mess, or it's a giant mess that usually involves another massive kind of code base. But we know that we're already a long way from the black hole, and we know that most of the gravity is from the central black hole itself. So how do we do this? So how do we take into account the self-gravity of the star? And the trick is to write the metric in the form of a small perturbation. So you say the metric is some background, g mu nu. So for example, a Schwarzschild metric and some small perturbation. And we say that h mu nu, the magnitude of that must be small compared to the background metric, g mu nu. So g mu nu, for example, could be either the Kerr or, Kerr or Schwarzschild metric. So Kerr metric describes a spinning black hole. It's significantly more complex than the Schwarzschild metric, but all you really need to know is, again, you can write down the metric in, in a set of coordinates like this. You can write it down in Cartesian coordinates, and you can use that to compute these things analytically. So Kerr metrics, no, not really much more complicated. The expressions are a little bit longer, but the principle's exactly the same. So a spinning black hole is not really more challenging than a non-spinning black hole. Just the expression is a little more complicated to write down. Okay, so, but how do we express this this perturbation? So the good way to think about it, so if we only had Newtonian gravity, so if there was no black hole, we would have basically we would have the Minkowski metric. So Minkowski metric would be -1. I'm just going to leave a blank space for a moment. C squared dt squared plus dx squared plus dy squared plus dz squared. And well, it's pretty well understood that the way that you added, you take the Newtonian limit of Einstein equations is you add a small perturbation here, which is like the Newtonian gravitational potential. Now, more strictly, if you want to go close to the speed of light, there is a term in here, which is a kind of, it's a term of order, v on c squared. But this term does become important if you want to do Newtonian physics near the speed of light. But we are pretty happy neglecting that term. So this basically means that we have a metric perturbation. So if you want to write this as a metric, we can think about that's like a perturbed Minkowski metric, but you can perturb the Schwarzschild metric exactly the same way. So we could just think about, for example, adding this term, we could simply add a -2 phi over c squared into our Schwarzschild metric up the top. Now, because it's a small perturbation, you don't need to take into account everywhere, so we can simply take it into the G0 component of our perturbation, and this can be 0, 0, 0 everywhere else. So our perturbation can just be in the time component of the metric. And since we know that h mu nu is much less than g mu nu background, we can neglect h mu nu everywhere except for the derivatives. So we can say basically that the potential is small, but not necessarily the gradient of the potential. So for example, in our momentum equation, sorry, I shouldn't use arrows. Pi dt, we have a -1 over rho star ddxi of square root of -g pressure. That's the same as before. But then we have, well, we got this term which involves gradients of the metric to rho star t mu nu. So we have the regular term, which is like a dg mu nu dxi background now. And we've got an extra term, which is the gradient of our little perturbation, dh mu nu dxi. Okay, if we expand out, so this extra term, we get dpi dt. Let's just consider the self-gravity term, so just this term alone. So the extra bit, it's equal to half of u naught v mu v nu dh mu nu dxi. Okay, so that's neglecting some higher order terms. Now, but of course, the only non-zero component of our h mu nu is the naught component. Okay, so that gives us a half u naught. Now, v naught is by definition dt dt, which is 1. So these things become 1 and 1, and we get a dh naught naught dxi. So in other words, we get a minus u naught d phi dxi in the end. Okay, so in other words, if we are happy to take ourselves as being sufficiently far away from the black hole, that is literally the same as our Newtonian gravity term that we had before. So we can simply add the Newtonian self-gravity as a perturbation to the metric. And now we can simulate tidal disruption events. So I've kept the discussion general, so I haven't really talked about the way we discretize the pressure gradient. And the reason I've done that is because it's actually no different to what we usually do. So the rest of the method doesn't change. So for example, if we're simulating the fluid on particles like we do in SPH, so SPH is called smooth particle hydrodynamics. It's a way of simulating a fluid on a set of moving points. So for example, in SPH, we use, we have a set of points with a fixed mass, and we move them with dx I dt equals vi. And then we solve, for example, our pressure gradient is some kind of interpolation that sum over neighboring particles to get us the gradient in the pressure. But again, those aspects are not different in GR to doing it in not GR. So I tried to draw out what's different when you want to do things in relativity as opposed to doing things in Newtonian gravity. So I hope that's all clear. I hope we've got time for some questions. And Fitz and Meg are going to, well, hopefully you got computers set up from this morning. I'm going to take you through some practical examples in the afternoon. Thanks very much. So I might just switch back to the.
Yes. Can you? Yeah, I think there was some clapping of the hands, so we just have some technical issues with the audio. So yeah, I think we have time for a few questions. Anybody has anything?
Yeah.
Yeah, maybe you can check the chat. There's a question on the chat. Meanwhile, I'll try to plug in the audio again.
The chat's just disappeared, so if you can repost your question, because I just signed on a different device.
Yes, I can read. So one question was that I think 20 minutes ago, roughly, that this might be a naive question, but there's a problem with, but is there a problem with not being completely covariant when only integrating over the spatial dimensions?
So everything is completely covariant here, as in the equations of fluid dynamics would look the same if you took a Lorentz transformation, which is what you mean by being covariant. So, and that's kind of the point of these conserved quantities, is they are the things that are coordinate independent conserved. So that's, I guess that's why when we integrate over the spatial dimensions, what we're really doing is just putting that factor of the square root of minus g out the front. You know, we're kind of including that in the variable rather than including it in the dv. But the whole point of defining these conserved quantities is they are the things which are covariant. Covariant, if people who aren't familiar with the term, just means you know, same to all observers. So if you take a Lorentz transformation, you boost into another frame, you're going to get the same equations back again, or the same integral back again.
Thanks. I think maybe I have a naive question as a follow-up. So first, I think in your disruption radius, I think it's the other way with the mass ratio. And the other thing I was wondering...
Yeah, I did try to derive it. Sorry, it's equal density. Yeah, I'd times by radius. Yeah, sorry, it should be mass divided by, because it's density thing. So it's mass divided by volume. So yes, I got the masses the wrong way around. I confused myself. Yeah.
No worries. I mean, the other question I had is that I think there's like a, maybe you can tell me something about that. There's like a big difference between having like a TDE around 10 to the 6 black hole and 10 to the 8, because then, you know, your Schwarzschild and radius will be comparable. So is there like a way to do it? Is like any difference in terms of like simulating that?
So no, the simulation wouldn't be any different. I guess it would just be a very boring simulation of a star around a 10 to the 8 solar mass black hole, because it would just simply enter the event horizon. And you don't actually, I didn't quite cover that. So the question is what to do. So that if we simulate a star going to a black hole in the Schwarz geometric, so you may know that in the Schwarz geometric, the problem is the coordinates can't cross the event horizon without blowing up. And so that does mean we have to remove, you know, so things that would go into the black hole, we have to remove them before they actually enter, which is not really a problem because the last stable orbit in the Schwarz geometric is outside the event horizon. So, you know, you kind of know that anything within, say, 6 GM on C squared will plunge into the black hole. So it's very likely that, and it's very unlikely that anything that goes in that last plunging radius would actually come out again. So that's that's not a real problem. But there are other approaches. So people doing, for example, the GR hydro codes, a lot of them tend to use these fancy coordinates. So like the Kerr shield coordinates is a set of coordinates that kind of smoothly crosses the event horizon. So you only delete material once it's actually inside, which is a nice property. But it has the bad property that it's kind of hard to interpret what your coordinates mean, because they don't go to an observer that's got a Minkowski metric at infinity, which is a bit weird.
Yeah, okay, thanks. I just mentioned that because I think last year I was visiting Europe, and Tejo had like a work that he done some simulations of the D around like an almost into the 8 solar mass black hole. So you had some fun things to look at.
Yeah, I mean, it's a good idea. But so like entering the event horizon isn't particularly glamorous. Like you just go in and that's it. But you could do a simulation where you'd fully cross the event horizon and you could only delete material once it's actually inside the event horizon, which maybe for those cases might be more interesting.